Let's start the second session now. I invite Professor Guru Rao to chair the session.
Thank you, Professor Arunan, and we have 3 speakers. As has been the culture all along in this meeting, we request the speakers to keep to 25 minutes talk and 5 minutes discussion. And of course, I was the one who violated it in the very beginning, but I would suggest that this violation does not happen anymore. So I have the pleasure of inviting my good friend Professor Jemmis. He talks about continuum in hydrogen bond and other weak interactions, shift in XZ in the XZY, stretch from blue through zero to red. So he's going to take through our VibGyR of our spectrum. Dr. Jemmis.
Thank you, Professor Guru Rao, for this kind words. I begin with this title, but before I begin, I want to thank Professor Arunan for many things. One is to take the initiative to get a special issue of the Journal of Indian Institute of Science on the occasion of the 100th year of its existence, and also note that hydrogen bond has a similar celebration year, and so to have this special issue and to invite me to contribute, even though I haven't really done much in this area. So it was a review of something that we have done that I talked about, and I will briefly tell about the plan of the talk, because I don't quite know where I will stop. So I will begin with acknowledgement anyway. See, there is the usual hydrogen bonds, the red shifting kind, and then there came the blue shifting kind, and we were looking at this, and there was some way we got interested in this problem, which has nothing to do with hydrogen bonds, really speaking. And then I will try to give some general view of the explanations for this, making drastic approximations, and try to hint at the problems that is there when one goes from hydrogen to rest of the main group elements, and even bigger problems when we go from rest of the main group elements to transition metals, and see whether there will be a transition metal M bond that is possible. And that's probably where I probably may not reach much of this, and I will make approximations of unusual kinds. I thank, of course, Professor Arunan for this opportunity. These are the people who are involved in the process of our studying hydrogen bond over the years. Started with Jiju, Jorli Joseph, Jyotish, Jose, Vidya, Ginny, who helped in writing this review for Journal of Indian Institute of Science, and Professor Vishwanathan to give us confidence early on that he could actually get experimental evidence for something so feeble that we observed in 95 computationally. Well, only Ginny is here of this group of people who helped us. So, I am probably introducing these things which are talked about many times in yesterday. So, we usually have the generally accepted idea: if you have an XH bond and it forms an additional interaction, whatever way we describe it, then XH is most likely going to be weaker in the process. So, if it is weaker, then if you are looking at the XH stretch, it will shift to the red, right? That is quite normal, nothing unusual. We of course know that usually X is more electronegative and Y is also electron rich and electronegative. It's a whole range of it. I just put NHO, it could be anything else. Now, if you take this idea and say, okay, as a function of binding energy, that is the hydrogen bond energy, and if you were to look at the red shift, one anticipates that the red shift would increase if you have stronger hydrogen bonds, and if you don't have any red shift, we are at this point where infinite separation, there is no hydrogen bond. So that is the usual accepted idea, and nothing wrong with it, and there are large number of explanations, and one that the MO theoreticians initially gave, and of course it is not fully right, it's a partial story. It says though the electron density from the Y that has the lone pair is donated to the sigma star, and that gives the stabilization. If it does give the stabilization, of course this becomes longer, and so this is indeed the partial story, as Professor Arunan has given in this cover picture of this special issue, each one could have a different explanation because we are only seeing part of the problem. Now the problem, well, nothing unusual in this. I just gave this idea more to tell that this is so much etched in the mind. This line is not any holy line. It's a scatter of points all around. But there are some observations that forced people to think that perhaps when the hydrogen bond is very weak, as it happens in XH where the X is not very electronegative, then the XH bond becomes shorter, and yet there is the hydrogen bond. I mean, it is it is counterintuitive. I mean, there is no question about it. What it means is that somewhere along the path we should have points which will show that after the hydrogen bond formation there is a blue shift. It has become stronger. I mean, this is crazy. I mean, I thought it is funny that this is not possible, but how did we get into the problem? I mean, I was not interested in a hydrogen bond, and in fact I was quite aware of hydrogen bonds because I had a colleague, I have a colleague still, a distinguished colleague of mine who has also an article in this, Professor Deshiraju. I was sharing the next door with him for 25 years, so I was clear about the implications of hydrogen bond, but I never had any specific interest. But there was an X-ray structure that was published 25 years ago, and it was kind of unusual. It was unusual for the following reason. This is an acetylene substituted by gold. In this, there were two chloroforms trans to each other interacting with this pi bond, and there is another structure where there are 4 of them, and it looked to me that is very strange. There are 2 pi bonds, and yet the chloroform prefers to somehow be attached to one pi bond. The other pi bond is left free, and so this is a X-ray structure from INGOS. Then I felt, let us look at this. Is there anything so specific about 2 interactions with 1 pi? And so we looked at this, and we found that if one were to take a gas phase study or a theoretical calculation in the isolated system, whether it is CH3Cl or CH2Cl2 or CHCl3, in all of them the more stable arrangement is to have each of the CH interacting with the 2 different pi, but the difference between the cis and trans, if that is the way to put it, is small, and in an X-ray structure it is very likely that you get, for packing reasons or whatever, a trans arrangement. So this was interesting, but we did not quite spend much time on this. But when we were looking at this, we had calculated also the monomers and looked at this CH distance more closely. We are talking about 94 and 95. We found that somehow the CH is a little shorter than the CH in chloroform itself. Initially we thought we will leave it, there is nothing very unusual, but then at different levels we calculated and it persisted, and then I thought, oh, this is something interesting, we should publish this, but then I thought again we should get somebody to prove this experimentally, right? And then Professor Vishwanathan from Kalpakam was visiting us in Hyderabad, and I said, is it possible for you to have a look at this? And he said, it is possible, but it will take time. The time it takes is that he was just starting to set up a super cooled nose jet expansion arrangement. In other words, to get a very cold surface on which you can deposit CHCl3 and then look at the surface IR. So he did this, it took a while. I met him in 96, it took 2 more years, and we got this and published this in 99, and a few more things that was computationally possible that was done. Even at that time I did not think so much about this CH blue shift. I said, okay, it is blue shifted, so what? There was nothing nothing as unusual, I felt, and it was told, my student felt it's unusual, blue shift means it is somewhere here, the interaction energy is less, so it means that there might be a possibility that we might have a hydrogen bond with no shift and yet a definite energy, right. But again, it was not thought to be so important that we should detract from our own research in other areas and come to this. Then in the next 10 years, every year there were a large number of publications coming in telling that there is this blue shift for the XH bond. And what was even more interesting is that as Professor Arunan has given in this cover page, each one gave a different explanation, and each of this explanation is partially right. There is nothing wrong with one of them, except it is not a complete explanation. In fact, even more explanations are there. In my group, we even thought that it might actually be a result of long range electron correlation. What it means is, we have the XH group, X has lots of other atoms and electrons, and the acetylene part has large number of substituents, and you bring it to an equilibrium distance within quotes, and then one might try to increase the long range electron correlation attraction between atoms that are on either end of this molecule by bringing the distances closer, and one way of bringing that distance closer is by decreasing the CH, right. So all kinds of such explanations were possible, and I like this so much that this really tells us many things. And then I said, this was in 2006, a new student joined, and I said, let us have a close look at it. So he looked at many computational points and many experimental ones, and found that yes, there has to be a distribution, and at some point we could even find something like this. Details of this is published. It's a long paper, but we have explanations given, and I am not going to talk about this. It's a lengthy arrangement, but what is important is that we could have 2 points here, and these 2 points will give the idea that as the hydrogen bond energy increased, right, the blue shift actually became larger. At the same way, if you are here in this region, we will have 2 molecules, let us say 2 complexes, where the hydrogen bond energy is actually increasing, but the blue shift is decreasing, right, and of course a point here where we could have a 0 shift. So there is a whole range and possibilities are available. I will just give 3 examples more to tell that there is nothing so very unique about a blue shift. It's a question of equivalence, interplay of so many different parameters that we have in this as variables, and it's just that. So let us take 3, and what I will do is I will try to keep this distance at various intervals and optimize everything else and see what happens to the CH bond and also the hydrogen bond energy, in other words the minimum. So if you do that for benzene and CH4, let us assume that we have kept various values for the HY, Y being the center of this ring, and optimize everything else, and you find that of course the total energy, as you decrease the distance, it comes down to a energy is blue, it comes down to a minimum and it goes up when you go further. On the other hand, if you look at the CH, it starts decreasing, the CH length start decreasing, and very close to the minimum energy it is it's only slightly different. The CH distance in the free molecule is this. You don't worry about this large number of decimal points added, because this is computational one, and you find that sometimes the variations are so small. So do not put a lot of meaning into these numbers. I still wanted to keep it this way. If you do this for CH4 NH3, more familiar system, you find that yes, the energy comes down very quickly and we have a minima here. The CH distance also comes down, and at the energy minimum the CH is slightly longer, only slightly longer. So it is as though the parameters whatever is involved is only very slightly disturbed, and it becomes a red shift. If you go back now to another system, chloroform with benzene, you find that yes, the total energy comes down, the CH corresponding value of CH has a minimum value just before reaching the total energy minimum, but at this point interestingly it is still much lower than the value in the free molecule. So there is something which tells that okay, it could have been just slightly different, then the results would have been difficult. Now variation of such small magnitudes in CH is not just the result of hydrogen bonds, it is observed in many places. Let us take CH4 1.0919, take CF3H, we have not done anything, no hydrogen bond, another molecule, and it has already become shorter, right. This is true experimental computation, it does not matter. If you take CH3CCH, that is acetylene with a methyl group, propyne, the CH is 1.067, acetylene is 0.677, fluorine it becomes slightly shorter, not much but slightly shorter. Let us take ethylene 1.085, fluorine substitution it decreases it a little, 2 fluorines does it slightly better but not a big change. Now it is not as though fluorine substitution will always decrease a bond. You consider here water and FOH, here it has become longer, right. So one could see already looking at these individual molecules effects of substituents. It is not as though it is only in hydrogen bond there is this variation. Hydrogen bond has also opposing effects, so to speak, in this. I don't know whether I should skip this. Okay, let me very quickly, now that you know the pattern, right, we are essentially getting the dimer and then the scanning of it at different distances, you find that yes, OH, essentially the distance goes up, the minima, at the minima there is obviously a longer OH, and so we have redshift. We consider NH3, we have a redshift because it is already increasing, so it has to be a redshift. We go to CH4 water, it is decreasing and at this point it has started, so it has to be a blue shift. With ethylene a steeper shift, and so we say blue shift. So it looks as though at the beginning point itself from a long distance there is a decrease. Now this gives one some courage and also the liberty of a theoretician, because we saw see different people see the elephant differently, right. I am seeing it from a much longer distance, I mean smaller and smaller, it is almost like a sphere. I mean for me the whole thing is like a sphere. So if I were to approximate the elephant as a sphere, right, I mean this is a drastic approximation, and if that is the kind of or level of approximation that I would like to make, then I have one simple model to talk about in hydrogen bonds, right. Fully granted that this is the 0th level approximation from a long distance. Now what is this? Let us consider water, right. We have the OH bond polarized, H is plus, O is minus, I mean, and we have already a distribution of electron density that way, and I have intentionally made this a hand drawing to show how approximate this is, okay, so that there is nothing, it is not from any computation, it is my hand drawing, right. And let us bring a molecule like ammonia here, right. It kind of has a polarization effect on this bond. The polarization effect pushes this electron density even more towards oxygen. So the OH becomes even more polar, right. There is a stronger electrostatic interaction or whatever else that you can think of, but the process makes it longer. The electron density is going more to oxygen. Now how does the other one work? CH, carbon and hydrogen electronegativity differences are common, so the electron density is around carbon and hydrogen, also in the middle. And let us consider this hand drawing, so I could do whatever, right. Hand drawing, you bring in a ammonia, it kind of pushes the electron density a little away still. In both cases it has pushed it away and it has possibly got more electron density now within the CH bonding region, right. And so I say okay, there is small electron density in the CH bonding region, there is a stronger bond, right. This can happen in situations where carbon and hydrogen or X and H have very little electronegativity differences or a more uniform distribution of electron density. Now this, I mean, we tried this explanation for many systems and roughly works. There are examples where this argument does not fit so very well, okay, because according to this CH into anything else will always be blue shifting, which is not true. So it is not a 100% acceptable explanation, but something that helps immediately. We could get many examples at this point, and I come back to this. I really love this picture of Professor Arjun. I come back to this because we have this drastic approximation. If I were to now go to all of the main group elements, right, this is not complete, okay. If I go to all of the main group elements, we have studied a lot of them, with halogens, chalcogens and so on, and what we realize is we have an elephant model, and now we have the whole zoo actually. Each one is so different, and you try to make this approximation again, right, it becomes harder and harder, but it is good to have some approximation that helps us move. The best approximation that we have is the sigma hole, but even that, to know whether there is a sigma hole, you have to calculate, right. I want to avoid this calculate and get this. This is a very good one, but if you were to avoid the calculation and do it, well, first of all you have to do all kinds of calculations. We did all of these for a large set of halogen bonded systems first, right, and in that large set of halogen bonded systems, well, I skip this number, it is not worthwhile. One could go through this similar kind of an exercise just for halogens. We have done this for chalcogens and decagens and so on. When we do this, we find that there is nothing so very dramatically different from the situation that was there in the hydrogen bond, except the variables are more. What are these variables? See, I am not even going to explain the curve, because you have a feel of seeing the curve itself. If it goes down and goes up, then you have a chance for blue shift. If it goes straight, it is a red shift. So this is blue shift obviously, and we collect all of these things that are there from experiment and computation. You get a picture like this. There are examples of this kind. In fact, there is one which is so very close, it is as if there is no shift, but the interaction energy is not small, about 2 point some kilocalories. So it is not something small, but there are larger blue shifts than what is possible in this. One could do this exercise for all of them, and you can get, I will combine them together, something like this, and we have explained qualitative ways of getting to each of them. But what is interesting is there a way that we can now get a approximation? This is 4 spheres, but if you go still farther away, there is only one sphere. Okay, so the different animals into one model. Now that one model obviously is not a very successful model, but I would still like to keep this model, because this model is based on hyperconjugation, negative hyperconjugation. Like in a system like CF3Cl, you have the negative hyperconjugation of this lone pairs on the chlorine going to the sigma star of the CF, the lone pair on the fluorine going to the Cl sigma star of CCl, and a combination of this possible depending on different molecules, right. And if we take that as the major one, we have a possibility. Now I take this model as a practical one. I skip the details because I see that I am getting close to this, but in this what I would like to say is that extension of Z bond from hydrogen to the others gives us far more variables, and the beginning monomers, the starting XH bond or starting XZ bond, its distance itself is almost deciding whether it is going to be blue or red. If the XH or XZ bond is very short to begin with, then of course it will be red shifted. If it is very long, then it will be blue shifted, which is not to say that there is no role of Y. There is a role of Y that gives the final distinction. Now I have the in the 30 seconds to say what happens with the transition metal bond, and you look at, it's like the unicorn, it is not there, right? So why is it not there? Is there any reason? And we thought that there should be some reason. So we looked at 300,000 structures from Cambridge crystallographic database, looking for an 18 electron regular transition metal complex and see whether there is one weak interaction even which can be described as a metal bond. That is 18 electron system, right? Donating that, accepting that as from another, let us say NH3 or whatever, and there is none, and that was surprising. We have gold and silver, that group, that is the D10 systems. D10 systems would have this, but anything that is a regular transition metal complex, a D6, D7, D4, whatever, an 18 electron complex giving an additional bond chance, that is not there. So we are talking about an animal that we haven't seen and yet speculating. At least the elephant we have seen and then we can speculate, but here we are speculating about something that we don't even know, but we did, and there is an article that is there in the recent issue of Journal of Chemical Science, which is dedicated for hydrogen bond, the periodic table, where we could talk about not just hydrogen bond, all the ones. And what I would like to say is that I'll skip all of these details. All it means is that we just tried and tried, we couldn't get any. But can we do something more? We found one thing. There was the sigma hole idea that was there for halogen bond and all the other main group bonds. That idea is a hint. It's a hint so strong that when you look at any transition metal complex, the chance of getting a sigma hole is so little. In fact, you have to really look carefully. This is just a drawing that we have schematically made, but it is almost impossible to get a regular 18 electron transition metal complex to have a sigma hole in any direction. There are reasons for it, which we have discussed. Can we design? We have 2 or 3 candidates where there is a possibility to have a transition metal bond in the sense of hydrogen bond weak interaction. Well, I think I will, well, let me not dwell so much on the conclusion and conclude before I get the warning from the chairman. I would not like to spend even a minute more than what is given to me. I will thank again Professor Arunan for this, not just this this conference, but for the whole idea that there is hydrogen bond having an anniversary, there is Journal of Indian Institute of Science having an anniversary of a bigger kind, and the two together, and then get to a stage like this. Of course, my students, in fact Ginny might be there in the audience who wrote this article. Indian Institute of Science is represented by this building, and this is IPC. If you look at this building from IPC, it looks like this, and I thank you all for your kind attention.
Thank you, Jemmis, for this wonderful talk. I also enjoy your artistic skills, and
I didn't started it.
You took it from an elephant to the unseen, whatever that animal is, the unicorn. I think it's an interesting thing that, in fact, more or less summarizes what we have in understanding covalent interactions. We are still at the unicorn level, which is pretty good. So we can still keep working. For the youngsters in the audience, it's a good opportunity to go, and I think there is time enough for 1 or 2 questions. I shouldn't be talking. 1 or 2 questions. Yes.
Yeah.
No, hydrogen bond as a equivalent of a coordination has been talked about much.
Yes.
If we can think about particularly the transient metal, which is coordinately unsaturated. That's what we had in the sense.
No, coordinately unsaturated will become a regular halogen bond of that element, not
so
the metal
we
bond.
need to have coordinately unsaturated with enough electron withdrawing substituents to make a sigma hole. That's just a
Yeah, in fact, there are large number of structures in the database which will be equivalent of the halogen bond with the metal or any other.
You remember the paper we had on FeCO5?
Yes. Yeah,
You can
that's
form
right.
hydrogen bond,
Exactly.
halogen bond. It cannot form an ion bond.
Yeah.
So you need to.
Yeah, that ion bond, the ion bond is just not there somehow.
Any other question? Well, if not, I just have a comment. The comment is that your handwritten diagrams are pretty close to the final electron density we get from charge density analysis.
Well, that's nice to know.
Very interesting.
That is nice to know.
Thank you very much for this wonderful.